Have you ever really stopped to think about what's going on inside your own head? I mean, it is an absolute storm of incredible complexity. But what if I told you that the big idea behind both your brain and artificial intelligence, well, it all boils down to some surprisingly simple math. Let's get into it.
Okay, get this. 86 billion. That's roughly how many neurons are firing away in your brain at this very moment. Each one is like a tiny computer, and together they form a network so vast that, yeah, it's pretty much the most complex thing we know of in the entire universe.
So the big question is, how on earth do we even begin to copy that? How do we get a machine to learn and recognize and decide things the way our brains just do? Well, this is the challenge that throws us right into the world of artificial neural networks.
So here's our roadmap for today. We're going to start with the brain's blueprint. Then we'll build a bridge from biology to math. After that, we'll look at a single neuron's very simple math. And finally, we'll see how it all comes together so a machine is learning to see.
Okay, first up, let's start with the original blueprint, the brain itself. I mean, nature has already built this incredible learning machine, right? So it just makes sense to take a few notes from its design.
Just think about it for a second. You didn't learn to recognize your best friend's face because someone gave you a list of if this then that rules. Nope. Your brain learned by seeing them over and over again. From experience, it adapted, it strengthened connections. And that right there, that's the core idea we're trying to copy.
And this whole concept, it has a name, biomimicry. Now, to be super clear here, we are not building a squishy biological brain in a lab. What we're doing is building a mathematical model that's inspired by the brain. At the end of the day, an artificial neural network is just a big set of math equations that copy the process of learning.
So, how do we build that bridge? How do we get from the, squishy world of biology to the clean, crisp world of numbers and code? Well, we have to translate the neuron into the language of math.
This right here, this is basically our Rosetta Stone for understanding this whole thing. On the left, you've got the parts of a real neuron. On the right, you've got their AI counterparts. So, dendrites, they just become numerical inputs. The axon, that's the output. But the most important one, the one I really want you to focus on, is the synapse. In AI, we call this a weight. And the best way to think about it is like a volume knob. You know, in biology, there's this classic saying, neurons that fire together, wire together. And all it means is that when two brain cells are active at the same time, the connection between them, that synapse, it actually gets physically stronger. That's the bedrock of how we learn and form memories.
So how do we mimic that in our math model? Well, it's actually kind of beautiful in its simplicity. We just change a number. That's it. If a connection is helping the network get the right answer, we turn its volume knob up. If it's messing things up and leading to mistakes, we turn it down. Learning for an AI is literally just the process of adjusting millions of these tiny knobs.
All right, enough with the high-level concepts. Let's get our hands dirty and actually look at the math inside one of these artificial neurons. And I promise you, it's way simpler than you might be thinking. It's really just a four-step dance. First, the neuron gets its inputs, just a list of numbers. Step 2, it multiplies each of those inputs by its own special volume knob, or its weight. And some of these can be negative, which is like turning the volume way, way down. Third, we add something called a bias, which is just a little nudge to make the neuron more or less likely to activate. And finally, step 4, we just add it all up.
And there it is. That's the thinking part of our artificial neuron. You take each input, multiply it by its weight, add them together, and then add that little bias at the end. See? I told you, it's just math.
So, after all that, we get a single number. In our little example here, it's 0.67. This number is basically the total signal strength bubbling up inside our neuron. But we're not quite done. The neuron has one last simple decision to make.
So, the big question, does it fire or not? This is decided by what's called an activation function, and the rule is about as simple as it gets. If the final sum is bigger than 0, it fires. If it's not, it stays quiet. Our result was 0.67, so, yep, this neuron fires. Okay, so one neuron doing some basic math is cool, I guess, but it's not super useful on its own. The real magic, the real power, happens when you connect millions of them together into a network. Let's see how that lets a machine do something really complex, like recognize a handwritten number.
A pretty typical network has, three main sections. You've got the input layer, which just takes in the raw data. Then there are one or more hidden layers. This is kind of a magic box where all the heavy lifting happens. And finally, you've got the output layer, which gives us the final answer.
So let's imagine we feed our network an image. This handwritten 7 gets broken down into hundreds of pixels, and the brightness of every single one of those pixels becomes an input number that gets fed into that very first layer of neurons.
Now the signal starts flowing into those hidden layers. And this is where things get really cool. Through lots and lots of training, different neurons have automatically adjusted their volume knobs to become little specialists. One might get excited when it sees a horizontal line, while another is looking for a diagonal one. Each one is looking for its own little piece of the puzzle.
And then all those signals hit the output layer. The neuron whose job it is to recognize the number 7 gets these strong signals from the horizontal line neuron and the diagonal line neuron. It basically screams, "Hey, I see all my parts," and fires like crazy. Meanwhile, the 3 neuron over here is waiting for signals about curves that just aren't there, so it stays silent.
And here is the absolute kicker. This is the most important part of this whole thing. We never, ever wrote a piece of code that said a 7 has a straight line on top and then a diagonal line. No way! The network figured that out completely on its own. By looking at thousands of examples and just constantly, tinily tweaking all those volume knobs, it learned the patterns. It literally taught itself how to see.
Which brings us right back to where we started. We went from the mind-boggling complexity of 86 billion neurons all the way to a system that's built on a foundation of simple multiplication and addition. It's just a powerful reminder that sometimes the most complex and amazing behaviors can pop out of very simple rules, just repeated millions and millions of times over.
And that kind of leaves us with one final big thought. We've seen that teaching a machine is really about tuning it, adjusting maybe trillions of these tiny mathematical knobs until the output sounds right. So the question we really have to ask ourselves is, what tune are we, the creators, teaching them to play?